Hello and welcome to our lesson on probability with counting methods. So just to recap, we have talked about three semi-quick ways to count the total number of outcomes possible in a variety of scenarios. We learned about the counting principle, which basically says that we can multiply. And what we're multiplying is the number of outcomes for each event in a scenario, and that product is going to tell us the total number of outcomes that are possible. And then we talked about permutations. Permutations, where we're still applying the counting principle, are ordered arrangements. They are ordered arrangements of R items chosen from a group of n items, and then no items are used more than once. So we saw how we could use the counting principle with those, or just use our permutation formula or calculation in Desmos. And then we've also talked about combinations. Combinations are similar to permutations, where you're choosing R items from a group of n items. Items can't be used more than once, but with a combination, the order doesn't matter. Okay, order doesn't matter. Okay, now we need to be able to possibly apply these three counting methods, maybe not all in one problem, but one at a time, when we're calculating a probability. So when we're calculating a probability, the total number of outcomes that are possible in a scenario, that's the bottom of our fraction, okay? The total number of outcomes that are possible in a scenario is the bottom of the fraction. Like when you're finding the probability of something happening, rolling a six-sided die. There are 6 different outcomes, 6 is the bottom of the fraction. Right? Or you're picking a card from a standard deck. There are 52 cards to choose from, so 52 has to be the bottom of the fraction. Now in some of the situations we're going to look at here, there are going to be a bunch of different things going on, or we're choosing a bunch of people from bigger groups of people, and so we're going to try to apply our counting principle, permutations, or combinations to figure out what that total is. And then we might also have to use one of those counting methods to determine the top of the fraction. Okay, and I'll show you with some examples. But before we get into that, I just want to distinguish a couple things, just to be ultra clear on where we were before and what we're going to be applying now. So let's just say we were arranging 4 books on a shelf. Okay, we've got 4 books we put on a shelf. If the order of the books matters, right, and we can't put more than one book in more than one spot on the shelf, then we can apply the concept of counting principle, permutation, or combination, depending on if order matters or order doesn't. So if the order matters, right, then we're going to call this a permutation. This is a permutation where if the order matters, or we could use the counting principle here, and I'll show you both. If the order matters, okay, if we're going to use the counting principle, we could just say, all right, there are, for the first spot, second spot, third spot, and 4th spot on the shelf. If we're going to go to put a book in the very first spot, we haven't placed any books yet, all 4 of the books could go there. Now once I've placed one book there, there's only 3 left to go in the next spot, only 2 left to go in the 3rd spot, and only 1 book left to go in the 4th spot. So according to the counting principle, 4 times 3 is 12, times 2 is 24, times 1 is still 24. There should be 24 different arrangements of books. Now that is exactly what the permutation would be here. The order matters, so permutation, we would say, what's the number of permutations possible when we're arranging 4 books from a group of 4 books to choose. And if we put that into the formula, it'd be 4 factorial over 4 minus 4 factorial, and 4 factorial, remember, just means 4 times 3 times 2 times 1, and then 0 factorial on the bottom is just 1. So we end up with the exact same answer. And all this work, just so you can recall, that's done in the calculator for us, okay? But all of this leads us to the exact same answer. Which was, 24. Okay? Now, if the order doesn't matter, we don't have the option of using the counting principle again, because if you recall, the formula works a little differently. We have to divide out the duplicates, right? Putting rearrangements of things doesn't create a new arrangement because the order doesn't matter. So here, the order doesn't matter. This is just a combination. Okay, it's just a combination, so this would be, what's the number of combinations when I'm choosing 4 books from a group of 4. Now remember, this formula was n factorial over r factorial and n minus r factorial. So in this one, it was 4 factorial on the top, 4 factorial on the bottom, and n minus r, so 4 minus 4 factorial here. So we end up with a different answer, right? We have basically these canceling out and then the 0 on the bottom. We're going to end up with 1, okay? One option here. So if the order doesn't matter, we can't just multiply 4, 3, 2, 1 in place of using our formula like we did over here, because the calculation is different. There's that extra r factorial dividing out. So if it's a permutation, we have the option of using permutation or counting principle. If it's a combination, we have to use our combination formula. Okay? So let's go back to our note sheet here and let me show you some examples of where this concept of finding the total number of possibilities is going to be incorporated with probability. Okay? So, for instance, problems that combine probability and our counting methods. So the first problem says 5 male and 1 female comedian each wrote a unique joke on an index card. The 6 index cards were given to the host of the show, and if the host plans on reading each of the jokes, what is the probability that he reads the female's joke last? Okay, so just important to note, now it's asking for probability. It's not just what are the total number of outcomes, and then we would just be multiplying and finding one number. Now it's a probability. And so with the probability, we're going to need a fraction, right? Something on the bottom, something on the top. So let's maybe don't write anything just yet. I kind of want to work through a few things with you. Let's just talk about in general here. We've got 6 total comedians, right? So total, what could happen? Well, all 6 of them could have their joke chosen first, and then only 5 left to go next, 4 left to go next, 3 left to go next, 2 left to go next, until 1 here, right? That is a permutation. The order that the jokes are told matters because they're all distinct jokes, so we'd be choosing 6 out of 6, okay? But what this question is asking for is what's the probability that the female's joke is last? So total, that's the bottom of the fraction, right, is taken care of. But what's the probability the female's joke is last? That's the top of the fraction, okay? So the top of the fraction, let me just change colors here. The top of the fraction, the female joke going last, that's what we're looking for here. So what we want then is for a male joke to be told first, second, third, fourth, and fifth, and then we want a female joke to be last. So if a male's joke is going to go first, there are 5 males that could be in that spot. So 5 of their jokes could go here, and then once one of the male's jokes is told, there are 4 left to go here, 3 left to go here, 2 left to go here, 1 left to go here. And then the female's joke has to go last. So there's only 1 female comedian. She only put 1 joke in the hat there, so there's only 1 option for her. That's the top of the fraction. And so we're going to make a fraction out of this, and that's going to tell us what our probability is. Now what's happened on the top of the fraction is 2 separate permutations. So first, this permutation, right, that was a permutation where we were arranging 5 of the 5 male jokes, and then this was a separate permutation right here. We're just arranging 1 of the 1 female's jokes. And if we have multiple things happening on the top, the counting principle says we could multiply those 2 and a fraction there. So we have the counting principle option here, and then we have the permutation formula option here. Okay, 2 different ways to go about this problem. Now I'm actually going to clear this out and do this again with you so we can make sense of it just one more time. Sometimes going over it a couple times makes it a little bit clearer. Okay, so we want, again, the probability that a female joke is going to be written last. So this means we want a male joke, a male joke, a male joke, a male joke, 1, 2, 3, 4, 5, all 5 of those male jokes to go first, and then the female joke to go last. So there are 5 male jokes, or 5 male comedians out of 6 total, right? Or once 1 male joke has been told, there are only 4 left out of 5 total, and then 3 jokes left out of 4 total, 2 jokes left out of 3 total, 1 joke left out of 2 total, and then there's just 1 female joke and 1 joke left total. Okay, that's going to give us our answer. Now that could all be typed into Desmos, but hopefully you're seeing where we can cross-reduce some things here. And so what's going to be left is 1/6 for our answer. I don't want to confuse anybody. You could definitely put that in a calculator, but you're going to end up with 1/6. Okay, so this is the counting principle option. Counting principle option. Or we could use permutations. So let me show you the permutation option. Permutation option. Okay, so the permutation option, the top of the fraction was two different things happening. First, we were looking at how many arrangements were possible for the 5 male jokes out of the 5 total that were there, and, so we're going to multiply, how many ways could we arrange the 1 female joke out of the 1 female joke that was there. And then on the bottom was the total number of arrangements for all 6 jokes from all 6 comedians. Okay, so either one of these. Now again, that could go into the calculator, and I just want to show you so I can confirm here. Let's see, I'm going to hit the divide to make my fraction. I have to go into functions, and I'm going to put my permutations, 5, 5 for the first one, times, again, functions, permutations, 1, 1 this time, and then on the bottom, number of permutations again, this time it's 6, 6. And I'm going to hit my little fraction in blue so that it shows me that the same answer happens, 1/6. Okay, so it's 1 out of 6 is our probability. Either option is available. It's sort of like whatever makes more sense to you. I tend to stick to formulas because the other route takes a little bit more thought, but it's really whatever is making sense to you. You just got to be careful because when we get to the combinations, writing out the fractions like I did in blue here is not going to be an option. We're going to have to use the formula. Okay, so let's try another. Let's see. A locker combination contains 4 numbers between 1 and 20, and none of the numbers can be repeated. What is the probability that the locker combination will consist of all even numbers? So hopefully again you can see how this is a permutation, right? The order in which you put the numbers in your combination definitely matters. A different order makes a different combination. So since this is a permutation, we can use our permutation formula. And then I'm going to go back and show you how to do this the other way too if you want. So the permutation formula, what's going to go on the bottom? Well, what we're doing is we're arranging, let's see, from 1 to 20. From 1 to 20 is 20 different numbers. So there are 20 different numbers to choose from, and we're trying to make a combination that includes 4 of them. So let me just sorry. I'm going to try to make sure you can follow later where these numbers are coming from. So we want 4 numbers, and we're going between 1 and 20. So on the bottom, it's how many arrangements of those 4 out of 20 numbers are possible total. Okay, that's the total. Now on the top of the fraction is what we're actually trying to figure out. We want on the top, the probability. So again, that tells us we need a fraction here. Here, let's, I'm making too many colors. Probability, that's why I have the fraction here. Okay. What is the probability that's going to consist of all even numbers? So even numbers, okay? So on the top, it's a permutation of how many even numbers are there? Well, 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. That's 10. Half of the numbers are even. So on the top, we're only looking at those 10 even numbers, but we're still trying to choose 4 of them for our combination, okay? And that's going to give us our correct calculation. Now if you would like to see this the other way, we want an even number. Let me go blue. We want an even number, another even number, another even number, another even number. So the first time we go to choose an even number, there are 10 even numbers out of the 20 numbers total. Now once that even number is placed, there's only going to be 9 even numbers left out of only 19 numbers total. And then there's going to be 8 evens left out of 18 total. And there's going to be 7 evens left out of 17 total. So I'm going to put each of these in the calculator just to show you that both are going to be options here. So let's see, first, let's go 10 over 20 times 9 over 19 times 8 over 18 times 7 over 17. Hit the little fraction button, and so we're looking at 14 over 323. Okay, so make sure that our combination or our permutation formula is working as well. So make the fraction. Permutations, and this is 10 evens. We want 4 of them. On the bottom, permutation, 20 numbers total. We want 4 of them. And again, let me hit the little fraction key. And there it is, the exact same answer, found 2 different ways. Okay, so this is the same. 14 out of 323. And now I'm using too many colors. Let's just highlight. Okay, and just because I want you to have good notes later when you come back to this, this was here, choosing 4 of 10 evens. And then here on the bottom, we were choosing 4 of 20 total numbers. Or 20 total options. Okay? Squished in there. I'm just trying to help you see what's going on, and hopefully this is making sense. Okay, let's try one more time, and then we're going to switch gears and look at some combinations. So it says here on the next one that Tom, Sally, Megan, and John are on their way to a meeting, and the sooner they arrive, the closer they get to sit to the boss, which apparently is a good thing at this meeting. We want to know the probability, so we're going to make a fraction, that Tom arrives last, okay? And the order matters here, right? This says the sooner that you get to the meeting, the closer you get to sit to the boss. So the order in which these people arrive matters, all right? So let me show you, I don't know which way you want to see this first. Let's go with, it says, what's the probability Tom arrives last? So Tom has to be last, but let's make an abbreviation here. Let's let A be anyone, right? Anyone. So anyone can be first, anyone can be second, anyone can be third, but Tom has to go last, okay? So anyone being either Sally, Megan, or John, any one of those 3 could go there. So there are 3 people out of the 4 total options that could be first. And then there are 2 left out of the 3 total options that could be next. And then there's 1 left out of the 2 total options that could be there. Now Tom is the only Tom, so there's 1 option for Tom, and there's only 1 option left total for that last spot. Alright, so this is going to get us this answer, and again, this nice feature happens here. That's going to end up being 1/4, although you could absolutely put that into the calculator. So this is going to be 1/4. Now, if you want to use the permutation formula, the permutation formula would be on the top of the fraction, what's happening? Well, 2 different things are happening, okay? 2 different things. First, we want these 3 people here, okay? And then a second thing is happening. We want Tom to be here. So first, what's the number of permutations of the 3 people, arranging those 3 people? So arranging 3 out of 3, Sally, Megan, John, that's happening first. And, so we multiply, we're trying to arrange 1 Tom out of 1 Tom there is to choose from. Okay, and then on the bottom, we are looking for the number of arrangements of 4 people, and there are 4 total to choose from. Okay, so if we put that into the calculator, we're going to get the same exact thing, and just so you can see it, just to confirm, oh here, I could manipulate this one. This was 3 and 3, 1 and 1, and then 4 and 4. 4, and there it is, the same answer of 1/4. So 1/4 here, and boom. Okay. Now, I tend to like the formulas a little bit better, but it's really up to you when you're looking at a permutation problem. In the next one, I think the actual counting principle is a little easier than the formula, but you can decide for yourself. So what's happening in the last one? What's the probability that they arrive in the order that's listed? So if they arrive in the order that's listed, that means it has to be Tom, and then it has to be Sally, and then it has to be Megan, and then it has to be John. Okay? So there's only one Tom out of the 4 total people. There's only one Sally out of the 3 remaining people. There's only one Megan out of the 2 remaining people. And then only one John out of the 1 remaining person that could arrive in that order. So that's going to be, let's see, 1/24. And again, that could absolutely go into the calculator. Or, now I need to move this. Or, if we're going to use our formula, it's, let's see, 1 out of 1 Toms, and then 1 out of 1 Sallys, and then 1 out of 1 Megans, and then 1 out of 1 Johns, and it would be 4 out of 4 people total. Okay, so either one's going to get you the same answer. Again, I think the permutation one's a little ugly there, but it's whatever makes more sense to you. Okay, so I'm going to go ahead and box this in over here. I don't really feel like typing that other thing into the calculator. Maybe you can just trust me or verify me that that's going to work. Okay, all right, so these are all permutations where we have either option. On the back, we're going to look at some combinations where the order doesn't matter, but that affects how we make the calculation. We can't just write out the fractions like I did in blue on this side. So with combinations, we're going to stick to our formula, okay? So these are all combinations. And for combinations, okay, you have to use the formula. And when I say formula, I don't really mean use the formula. You're going to let the calculator do the formula for you, but actually use the C, okay? So, a club, in this next example, consists of 5 men and 7 women, and 3 members are going to be selected at random to attend a conference. So, it doesn't matter which members you choose. It's going to be the same 3 members that go to the conference. Again, order doesn't matter. This is a combination. So, it says, what is the probability that the group selects or the selected group consists of 3 men. So the probability that it consists of 3 men. So we're trying to get a group of 3 men. That is the top of the fraction. So the top of the fraction is the number of combinations. We're trying to choose 3 men out of, there are 5 men total. So we're trying to choose 3 of the 5 men. On the bottom of the fraction, what's the total number of options? Okay, on the bottom of the fraction, the total number of options. Well, the total number of options is we're choosing 3 members from 5 and 7, 12 total members. Okay, we're choosing 3 members out of 12 total. Okay, so let me just read that again to you. On the top, this is 3 of 5 men, and on the bottom here is 3 of 12 total. Okay, so we're going to put this into the calculator, let the calculator do the formulating for us. Get rid of all this mess. Alright, so fraction, combinations, 5 and 3, and on the bottom again, combinations, 12 and 3. And let's hit the fraction button, 1 out of 22. So there's a 1 in 22 chance that this group is going to consist of 3 men. Okay? Next one, what's the probability that the selected group consists of 1 man and 2 women? So first, a couple things going on here. We're trying to choose 1 man. So we want 1 man. We're going to choose 1 man of the 5 that are available to choose from. And so we're going to multiply. We're trying to choose 2 women. So we're choosing 2 women out of the 7 women that are available to choose from. So that's what we want to happen. That is the top of the fraction. right? Now on the bottom, total, what's happening? On the bottom, we're choosing 3 people to attend this conference out of the 12 total, right? It should make sense for A and B, even though what we're looking for on the top is different, that the total number on the bottom is the same. It's like when you're rolling your 6-sided die. Whether you're looking for the probability of getting a 2 or even or whatever it's for, there's 6 options, right? So the bottom of the fraction remains the same. So this is, okay, 1 of 5 men. This was 2 of 7 women. And then this one was 3 of 12 total people. Okay, so we're going to put this all into the calculator. So let's see, let's go 1 and 5 times combinations again, 7 and 2, and then on the bottom is the same fraction, so 21 out of 44. 21 out of 44 is the probability there. And so which one's more likely to happen? Maybe it's hard for you to see those in comparison. Is it more likely that we have 3 men or more likely that we have 1 man and 2 women? Well, 1 out of 22 is about 4.5%, and 21 out of 44 is about 48%. So this one is definitely more likely. And again, just so you can have some reference here, this is about 4 point, here, let's make the decimal, 0.04, oops, 0.045, which is about 4.5%, and this one was about 0.48 or 48%. Okay? So just so you have some reference there, and remember when you're working on these things in your practice, it's probably going to ask for the decimal or the percent. So make sure you can convert. All right, let's try this again. It says, to play a certain lottery, a person must correctly select 6 out of 50 numbers. If one winning ticket is selected, what is the probability of winning? So the probability of winning, all right? If we want the probability of winning, we're going to be looking for the number of combinations of the one winning ticket, right? One winning ticket out of the, how many winning tickets are there? 1, right? So 1 winning ticket out of 1 winning ticket to choose from. That's all that's happening on the top. On the bottom is where we want the total, okay? So on the bottom, we're trying to correctly select 6 out of 50 numbers. Oh, I think I goofed on the top here. I sure did. Let's look at this again. So we're trying to get correctly selecting 6 out of 50 numbers. So on the bottom, we're choosing 6 numbers out of the 50. Hopefully that makes sense. What's the number of combinations possible? The order doesn't matter, so what's the number of combinations? Choosing 6 out of the 50 total. On the top, the one winning ticket is going to have all 6 of the 6 winning numbers. So on the top, we want the number of combinations of the 6, choosing the 6 out of 6 winning numbers. Again, hopefully that makes sense. Even I confused it the first time. So we're choosing 6 of 6 winning numbers. And then on the bottom here, right, it's 6 of 50 total options. Alright, so now it's calculator time. Alright, so calculator, fraction, combinations 6, 6 on the top, and then combinations 50, 6 on the bottom, and that is a tiny, if you're seeing that on the screen, that is scientific notation. Little side note, 6 point, when it says 6, I swear I said pen, 6.29-ish, whatever. When it says times 10 to the negative 8, that means the decimal needs to move 8 times in this direction. So there's going to be a bunch of zeros before this. Okay, that's a really small number. Let's see if it'll give us a fraction that's a little easier to write. And it does not. So that's okay. We're just going to have this redonkulously small decimal, which should make sense. The probability of winning the lottery, not so good. So let's see. This is going to be, Desmos says 6.29-ish times 10 to the negative 8. And I'm going to change this to approximately. I just really don't like this decimal. So this is going to be 0.1, 2, 3, 4, 5, 6, 7 zeros before the 629. I gotta sneeze. Oh my gosh, I'm so sorry. Excuse me. That one has been bugging me for like the last 10 minutes. Okay. Let me see if I can input this in the calculator separately so I can get a nice fraction here. I'm going to put the number of combinations on the top. That's just 1. That should make sense. There's only one winning ticket, right? And then on the bottom it was 50 and 6. And there's that giant number. So I put them in separately. It's going to be exactly 1 out of 1589070. That is 15,890,700. That's just crazy tiny, okay? So notice again what I did is I put those in separately because Desmos was having a hard time converting it to a fraction for me. So I did it manually, all right? Not the funnest, but there you go. That's probably realistic odds of winning the lottery. All right, let's try another one. Mike has 15 batteries in a drawer, but 6 of them are dead. I hate when that happens. My kids actually do this to me all the time. We've got a battery drawer in the house, and when they come to swap out new batteries for their PlayStation remotes, they just throw the old ones in the drawer. I'm like, guys, not helpful. Anyway, so Mike's got 15 in his drawer, 6 of them are dead. If Mike reaches in the drawer and randomly selects 3 batteries, what's the probability that they're all defective? I'm assuming that means dead. Let's, if they're all dead. So on the top is, we're looking for the number of combinations. We're choosing 3 dead batteries out of the 6 that are dead. Okay, we're choosing 3 batteries out of the 6 that are dead. But on the bottom of the fraction, what are we choosing? 3 batteries out of the 15 total. Let's make this 15 batteries total. That's why they're there. Okay, so we're going to put this in the calculator. This is 3 of 6 that are dead. And apparently I can't spell. Goodness. Sneezing, spelling mistakes, what's going on here? And this is 3 of 15 total batteries. Alright, calculator. Fraction. So we've got 6 and 3, and then 15 and 3. So please make me a fraction. That is 4 over 91. So 4 out of 91 chance of that happening. If you like the decimal better, where did I go? Undo. 4 to 91 is about a 4% chance that you reach in and grab 3 dead batteries. Okay, what's the probability that they're all good? So we want the combinations that we choose 3 batteries out of how many of them are good? Well, if 6 of them are dead, then 9 of them are good, right? And again, we're choosing 3 of 15 total. So this is 3 of 9 good live batteries, or again, 3 of 15 total. So into the calculator. All we gotta do is change this to a 9. And now we have about an 18% chance. So 12 out of 65. And an 18% chance, that's a better probability or a higher likelihood of choosing all good batteries, and that's because there are 9 of those versus just 6 dead ones, so it makes sense that the probability is a little higher. Alright, we got one left to give a shot here. It says for the last problem, and if you're feeling pretty good about this, pause the video, give it a try, see if you can figure it out otherwise. The staff at a restaurant consists of 25 people, including 8 waiters, 12 waitresses, and 5 cooks. For Mother's Day, a total of 9 people will need to be selected to work. If the selections are made at random, determine the probability that we have 3 waiters, 4 waitresses, and 12 cooks selected. So we have 3 different selections. That's 3 sets of combinations that are going to have to go on the top of the fraction. So first, we're going to choose 3 waiters out of the 8 that are possible. So for the waiters, we're going to choose, or find out the number of combinations when we choose 3 out of the 8. And let's multiply. Let's see, 4 waitresses are going to be chosen out of the 12 that are available. So for waitresses, looking for the number of combinations when we choose 4 out of 12. And so we multiply. We're going to be choosing cooks. And there are 2 cooks, or we're going to choose 2 cooks out of the 5 that are available. So for cooks, we're going to look for the number of combinations when we choose 2 of them out of the 5. Now on the bottom of the fraction, total, what are we doing? Total, we're choosing 3, 7, 9 people. Okay, we're choosing 9 staff, I guess, out of, yeah, there's our total of 9. And then out of the 25 that are available. So total is choosing 9 out of 25. And inputting that into the calculator is going to give us our answer. Alright, one more time. Let's see, 8 and 3 times 12 and 4 times 5 and 2 on the bottom. 25 and 9, and there it is, about 13.5, 14%, or that fraction, 1,008 out of 7,429. So that's going to be our exact answer. Or again, just so you have some variety here, this is about 0.1357 or 13.6%. Okay, so hopefully that makes some sense. Give it a try on your practice, and as always, if you find yourself struggling, reach out. I'm here to help. Alright guys.